가방 안엔 굳은 다짐이 the backpacker 우리는 backpackers yeah we the backpacker 내가 묻은 신발이 바래져도 backpacker 우리는 backpackers 출발은 언제나 겁없이 시작부터 맨발 내 눈에 싹 다 basic 보다와의 step pipe 펴진 내 black tie 프로젝트만 necktie 기본이 안 돼 있는 stupid I'm ready to fire right ambition is
Whoa, that track is so loud. We can really feel the ground shake when it passes.
Yeah, traditional trains can be noisy and shaky because of all the metal wheels graining against the tracks. That's caused by friction and vibration.
I guess we've gotten used to it. I can't imagine trains being silent.
Actually, there are trains that are almost silent. Maglev trains. They work using magnetism.
Magnetism? Like how magnets stick to a fridge.
Kind of. Maglev stands for magnetic levitation. Instead of wheels, the train floats above the track using powerful magnetic forces. You know how like poles of magnets repel each other?
Yeah, like when you try to push the same sides together and they won't touch.
Exactly. That repelling force is what lifts the train off the track. With no contact between the train and the rail, there's no friction, so it moves super smoothly and quietly.
That's amazing. So it just hovers and glides?
Yep, and it can go incredibly fast too. Some maglev trains even reach speeds faster than airplanes on short routes, all thanks to magnetism.
Now that really sounds like the future. No more noisy trains wrecking the whole ground.
For sure, maybe one day we'll have maglev stations right here.
Magnetic levitation train. For the role of magnetism in magnetic levitation train is lifting the train. The train is lifted off the track using electromagnetic or superconducting magnets. The pulsive or attractive magnetic forces create a gap between the train and the guideway. This eliminates with track contact and reduce friction to nearly zero. Other than that, moving the train forward. Maglev trains use a linear motor system. The track contains electromagnetic coils that are energized in sequence to create a moving magnetic field. This field interacts with magnets on the train to pull or push it forward. Last but not least, keeping the train balanced and aligned. Magnetic system continuously adjusts forces to keep the train centered above the track. Senses multiple position in real time, and the electromagnets react instantly to correct it or give this ensures a smooth, stable ride even at high speed and through curve. What happened with magnetism? First, no levitation. The train will lose its ability to float and fall onto the track. Passenger comfort and safety also will be compromised due to sudden impact. Next, no propulsion. Without functioning magnets, the train can't generate the forward or backward force needed for motion. The train would be stranded on the track, unable to move on its own. Last but not least, loss of stability and control. Failure in this system could lead to misalignment, causing the train to tilt, vibrate, or become unstable. For the benefits of magnetic properties, first, they are super duper efficient since there's no friction between the train and the track, thus energy is lost, and there's very little wear and tear on the parts. In terms of performance, magnet trains can reach very high speeds, over 500 km per hour, while still providing a smooth and quiet ride. Last but not least, they are also safer. Magnetic sensors and control system constantly monitor the train's position and speed, while magnetic brakes ensure a quick and smooth stop when needed.
Maglev trains use magnetic forces to float above the tracks called levitation and to move forward without touching the ground. This causes the train to float. No friction between the train and the track that allows the train to travel smoothly and very fast. The magnets also help the train move forward, called magnetic propulsion, and it will help it slow down when needed. By using magnets, the train can stop and start smoothly without using wheels. How they contribute to its functionality? First, let's start with electromagnetic suspension (EMS). Electromagnets are placed under the train that create a magnetic field that lifts the train without physical contact. These magnets pull the train upwards that attract to the steel track below. This keeps the train floating just above the rail that causes a small gap between the train and the rail. The train is naturally unstable, but the computers constantly adjust the magnets and use a feedback system to maintain the balance. Next is electrodynamic suspension (EDS). Uses superconducting magnets on the train. Coils are placed on the track that cause the magnets and coils create magnetic forces. These forces push against each other, that is repulsion, and make the train float. The train usually needs to move first before it can start floating. The magnets are kept cold using liquid helium that keeps them in the superconducting state. Let's see what type of magnet used and the role it plays in the maglev train. The first magnet that is used is temporary magnets. They are electromagnets used in the electromagnetic suspension EMS system. The role is they become magnetic only when electricity flows through them. So in EMS system, electromagnets on the train pull upward to keep it floating. The magnetic field strength is controlled by adjusting electric current flowing through the electromagnets. This helps maintain precise control over the train's levitation height. Next, the type of magnet that is involved is superconducting magnets, which are very powerful magnets made from special materials. Their role is these magnets are cooled to very low temperatures so they can work properly. EDS systems, they create magnetic repulsion between the train and the track. So as the train moves, this repulsive force lifts the train and keeps it floating above the track.
Levitation magnets is located under the train. These magnets repel or attract the track depending on the maglev type, causing the train to levitate above the guideway, eliminating contact and friction. Propulsion magnets installed in the track, usually as a part of a linear motor system. These magnets switch polarity rapidly in sequence, creating a magnetic wave that pushes or pulls the train forward, like a magnetic conveyor belt. Guideway magnets embedded in or alongside the track. Guideway magnets work together with the train's levitation magnets to create stable magnetic lift and maintain a consistent gap between the train and the track. One of the most famous examples is the Shanghai maglev train in China. It has been in operation since 2004 and can reach speeds of up to 431 km per hour. Another impressive example is Japan's Shinkansen, which uses superconducting magnets with speeds of over 500 km per hour. The use of magnets in these trains has a big impact on technology and society. Since the trains levitate, there is no friction, which allows for very high speeds and smooth rides. This also means maintenance because there are fewer parts that wear out. Maglev trains are also better for the environment. They are quiet, produce no direct emissions, and help reduce traffic and air pollution in big cities.
Our references. That's all. Thank you.